Bismillahirrahmanirrahim. My topic to discuss here is trends in non-contact structural health monitoring of CFRP composite laminates. Before I start my conversation, I thank you all the organizing committee of IBCAST, especially the Aerostructures Track, Dr. Abdul Rauf, Dr. Naim Zafar, Dr. Hafiz Sanaullah, Mr. Naveed, and all the other people who I couldn't name all. Thank you very much for providing me an opportunity to transfer and share my knowledge here. You have seen my introduction earlier, but here I will put my current research areas where I'm actively working. So first of all, I'm working in the area of laser ultrasonics as a non-destructive testing technique. During my PhD work, I worked for the entity of high-speed train axles using laser ultrasonics. I also work in FEA for various applications. I also train many organizations and people for commercial software, and I also teach FEA to postgraduate students in GIK Institute. Structural health monitoring is a research cum commercial activity which I'm following. Specifically, I'm following thermography. I have a couple of fundings. Where I'm working for thermography. Again, as a structural health monitoring technique for rail structures. And I have a PhD student working on thermography for CFRPs. I am also interested in EMATs these days. These are non-contact sensors for ultrasonics, and they are very much organized with new trends in SHM. The application these days I'm working on is railroads, of course CFRPs as well. I also work in the field of multi-body dynamic simulation, so it is related to FEA in a way. It works on Lagrangian dynamics. I'm also trainer of MSc Adams, which is a very well-known software for multi-body dynamics. So I also teach how to design and simulate mechanisms. And I'm also working on some research projects related to multi-body dynamics. I also work on UAV applications. So UAV or drones are very much into many activities all around. So I have many projects related to UAV applications, such as we are working on precision spraying for agriculture using UAVs. So it involves thermography and many other techniques which are already mentioned in structural health monitoring, and we'll talk about those today. I'm also involved in energy management. A part of it is energy audit and energy harvesting. So energy harvesting has a very strong connection with the new trends of IoT and machine learning. And energy harvesting is a part of energy management most of the times. And quite recently, I'm working on some research project with a local industry on thermal analysis of different applications. So today is the era of social media. So those who want to work on any of these areas, or they want to have some sharing of knowledge with me, they can connect with me on social media. So this is my YouTube channel where I teach all the activities and share the knowledge I have. And this is my Facebook handle where you can contact me for the activities I share. Similarly, LinkedIn is for professional connections. On Instagram for the new generation, I'm also there, and Twitter as well. So you can connect me anywhere you want. In today's discussion, I have distributed the content as follows. So the first of all, I'll talk about what is the relationship of non-destructive testing, condition health monitoring, and structural health monitoring. Then I will talk about typical defects in carbon fiber reinforced polymer laminates. And the detailed portion is the discussion of various SHM methods, and I will focus on how we can use them as non-contact methods for CFRP laminates. So let's start. In industry or in the design process, what is the common practice nowadays? So when we manufacture something and it has some design requirements or drawing requirements and process requirements. So based on those requirements, we do the non-destructive testing and see if the manufactured item is according to the specifications provided by the designer. So if it fulfills those requirements, we approve them and we start using them. And if there are some discrepancies, we either repair them or reject them until they are fulfilling those criteria. If it is functional and it has the requirements, we start using those products or processes. And after they are being used, we have different types of maintenance procedures in order to keep them in service. And there are various types of maintenance. So the first type, which is the very common type, is the reactive maintenance, in which when you start seeing a failure, you suddenly start acting. So when there is some problem, you act, otherwise you don't do anything. So that is the simplest way of maintenance. And many new products which don't have any qualified knowledge, they are acting under this. So this type of maintenance is also known as corrective maintenance. So when you see the fault, you correct it. Second type is the preventive maintenance. Preventive maintenance is a maintenance in which you have already maintained a schedule, and you, on that schedule, when the time arrives, you start repairing or making that maintenance. Like we have our vehicles, and we, after a specific number of kilometers, we change the oil, and we don't see the fault, but we know that after this much of kilometers we have to change the oil. So this type is maintenance is known as scheduled maintenance. The third one, and that is very much in nowadays, is the predictive maintenance. And as the time passes on and you keep on developing that product, you have a very deep knowledge of that product, and this qualification helps you do the predictive maintenance. Predictive maintenance is the maintenance in which you see the condition of your running machine or structure, and specifically if you're talking about the CFRPs. So you see the condition, you monitor the condition, and if you feel based on your background knowledge that this fault will hurt the functionality of that structure, you reject that, otherwise you keep on monitoring it. So this has a very small cost, but overall cost of the maintenance is decreased. So you don't have to, the number of failed products are reduced based on the condition. So even if at the time of the manufacturing you saw some faults, you still keep on using that object if they are not reaching a specific threshold. So this is a condition-based monitoring in which you have to do a lot of analysis and you have to keep many records, and it is a continuous process. And this is only reached when you have a very deep prior knowledge of that system. And the last one is the proactive maintenance, and this is a type of root cause failure analysis type of maintenance. This is something which you never knew in the predictive maintenance, and you saw a failure and you already had that condition-based monitoring. You had a very typical type of instrumentation available. You were constantly measuring all the faults or damages, and you know the time history of everything. So when that failure occurs, you have a sufficient data to further analyze that maintenance, and in the future you can improve maybe your preventive maintenance, or you make necessary actions to change your product specifications or requirements, and in this way you increase the in-service life of your product. So proactive maintenance, as an example, like we have the maintenance of we see if there is an aircraft accident, commercial aero industry, we see that there is a case open and they do a very deep analysis of that failure, and on the basis of that they try to relook into their procedures and they try to make the new ones. So this type of proactive maintenance and condition-based monitoring, they work hand in hand. And these maintenance have a very much deep relationship with the life cycle of product. So as the product becomes more mature, you have more control on the predictive and proactive maintenance, and you need to come into these two domains in order to have a increased service life of the product. So based on this new two types of maintenance, the new trend is like that when you manufacture something, you do, based on your further increased enhanced knowledge, you do the NDT, the non-destructive of that item, and based on your knowledge, some defects even which were the rejections earlier, you still accept them because they are below some threshold level, and that threshold level is defined by your experience that even that defect, a product with that defect will still work. So you will not reject that item and you'll see, let's take this product into service and we'll do the condition monitoring of that. We'll watch that product closely, and if the defect or damage reaches that threshold level where it is very dangerous to use that project, or there where this product is considered rejected, we will stop using it. So condition monitoring is reducing your number of rejections, so it is reducing the manufacturing cost with a very small cost per unit time of the service life of this thing. So ultimately this new trend gives you more control on the structure health of your project or product, and it also gives you more knowledge about your product, and it also helps you in changing the in-service life, the non-destructive methods, maybe testing methods or manufacturing processes as well. So you are in much control of all the life cycle of the product, and you can easily improve the life of your product. So this is the new trend, and based on this new trend, I chose I'm talking on the structural health monitoring. So basically, condition monitoring is different from structural health monitoring. It is the subset of structural health monitoring. So when you make something, you do the non-destructive testing. Non-destructive evaluation is also used. NDI, non-destructive inspection, is the another term used, and many people and authors explain them in different way. The basic principle is that you test something for its specifications without damaging it, so it is not destructive. That is non-destructive testing. So in the new trend, you still do the NDT, and when the product is in service, you do the condition monitoring, and both of these, when are seen at a broader spectrum, this is known as structural health monitoring. So structural health monitoring by definition is to measure and monitor the condition of something against the structure of something against some specifications, and unless they reach some threshold, you keep on monitoring it. So these two things are the subset of structural health monitoring. So even if there is some fault in the beginning, you still keep on using that product if it is under some specific threshold, and the condition monitoring helps you constantly monitor it, and if there is a problem, you reject it. This is something we do in the medical sciences, because if somebody is ill, we don't kill somebody. We do some data analysis, we do some testings, blood tests or CT scans, or many tests are done, and then we keep on watching those tests again and again, and we have some continuous monitoring sensors installed on the patient to see how he's behaving. And with the passage of time, we try to change the medicine and different treatment processes in order to increase his life. So same thing is being implemented on the structures now. So this is the base of structural health monitoring. Now let's see what are carbon fiber reinforced or CFRP laminates. So typically layered carbon fiber polymers are of two types. One is the sandwich composites, where you have a core, and the other one is the laminated composites, where you have just layers and there is no core. So we are going to talk about this one, this type of composites, which is very common in different applications of aerostructures. So different plies or layers of composites are connected together, and this collectively is known as a laminate. The manufacturing processes of these laminates are very important because these define the final characteristics of the laminate. The first one is the hand layer process, in which you put the resin inside the carbon fiber with your hands with a brush, and this is the simplest way of manufacturing the laminates, but it gives the lowest quality properties, and also it depends on the skill level of the person who is laying up the laminates. The second is the resin infusion, in which you use a compressor and to infuse the resin inside the carbon fibers using capillary action. So there are some tubes, small tubes, which are suck the resin from one side and pull and push the resin from the other side, and all the resin is equally distributed in the laminate, and extra is extracted out through the catcher. So this is the better method than hand layup. The third one is the pre-pregnated carbon fiber laminates, in which you have already the resin inside the carbon fibers, and you just use like stickers and apply and put the layers on the laminates and get your final property. This is the easiest one to use, but more expensive. It also gives you the good properties. Normally pre-pregs available in the market are need a very specific thermal cycling, and you need to have a good oven or autoclave to keep your products under pressure to get your required properties of the composites. But also some companies are producing out of autoclave prepregs, which are very easy to use. Then the carbon fibers can be woven or they can be unwoven. So woven carbon fibers are can have different textures of weaving, or unwoven fibers can be unidirectional or bidirectional. So for example, if you see here this pile, this laminate has one unidirectional laminates. So if it is woven, we don't know it, it's a simplified version. But woven carbon fibers all, of course, have their own properties. So this also the orientation of the composites is important. Fibers is important to define the final characteristics. So here you can see the fibers are oriented at 0 degree as compared to x-axis. The second ply is at -45, the third one is +45, and the fourth one is 90. So these orientations changes the properties of the components, and that is defined by the number of plies and these orientations. So both of these two things define the final properties of the composite laminates. So how you define what is the final strength you are going to get? This is based on the macromechanics of the laminate. So if you study the whole laminate as a single object, and you don't go to the micro level, you call it macro mechanics. And if you go to the fiber level or single ply level and you critically see at the micro level what are the characteristics of each ply, and then you build up the final properties of the composite, that is known as micro mechanics. So these two analyses give you the final equation, that what is the number of the final plies you are going to use and what are the orientations you are going to use. Okay, now we have seen that what are the CFRP laminates, how they are made and how they are designed. Now we see that what are the typical types of defects in the CFRP laminates. So we can divide these defects into three sub domains. The first one is the defects in fibers at the fiber level. So what are the defects which can be in the with respect to the fibers? So the first defect is the breakage. So the fibers may break. So if you have a fiber here and a fiber here and a fiber here, so this breaking of fiber is decreasing the strength of that composite in that specific orientation, and it is dangerous. So this type of effect can be seen. Another type of defect is the waviness. So waviness means that if you have fibers here, uh, the ideal situation is like this, but if you have fibers like this within the composites, so if they are like this in the composite material, so these are defects of fibers. So these will affect the functionality of your CFRP structure. Another one is the non-uniformity. So if you have a specific number of fibers in one direction and the density is not equal, is not uniformly distributed, so the strength of fiber will also be affected. So again, this is a defect. You want your carbon fibers to be equally spaced and uniformly distributed throughout your composite. Another fault can be on the metric, can be the improper orientation. Improper orientation means that if you see here, the micromechanics and macromechanics told that your orientation should be exact minus 45 degree, but while doing your hand layup or your pre-pregnated layup process, you by mistake put them at minus 48 degrees. So the final properties of this composite material will differ from the one you designed it for. So this can result in the defect because the real loading conditions will be different from the one you designed it for. So it can cause a defect. So this is another defect. So these four types are the basic defects in fibers. On the matrix level, the first is the contamination. Contamination means that while putting the resin inside, you had some foreign objects or some unnecessary things mixed in the resin. So resin has its own properties. If you have some foreign objects there, the place where that foreign object will be, it will change the properties in that specific. For example, if we have some sand particles here, so it will affect the property of your composites in that ply. So this is also a fault. Another type of fault can be the porosity and voids. So if there are some pores or air gaps within the resin, for example, typically in hand layup process, if you don't do it carefully, you will see some air gaps inside, and these air gaps can cause, for example, if there is a very small pores here, so these are the very favorite points for crack creation. So cracks will be initiated those specifically in the fatigue. So if the structure is under fatigue, small crack nucleation will be here, and those cracks will eventually end up in the catastrophic failure of this structure. It may happen. So if you are doing the conditional health monitoring, you will observe these voids in the beginning, and you will keep on monitoring those voids. So if this void is slightly increasing, your systems, your SHM will quickly tell you that there is a problem, and you will quickly reject that part if it is above the safe threshold. So porosity and voids is another problem in the matrix. The third one is the improper curing. So every resin, epoxy resin, has its own thermal cycling. So you have to cure it in that. Some are cured in the room temperature, some are cured in the oven, some are cured in a pressurized autoclave. So you have to follow those specifications. If you don't follow those specifications, the end product may have some humidity inside it, or it will not be properly cured, and when you will put it under the real loadings, it will fail. It may fail. So this is another problem in the matrix. The next one is the matrix cracking. So if you have the cracking within the matrix, it can be because of some other issues, like if there is some very small micro cracks available here. These are very smaller than voids and porosity, but these are micro cracks, and these micro cracks can initiate, propagate, and then result in the failure of the composite laminate. So these four are the common defects in matrix. And the third one is based on the fiber matrix interface. In this domain, the first one is the delamination. Delamination means that this ply is separated from this one. So this laminate is like this, and the other laminate is, separated from this. So this is delamination. So this type of defect is on the third domain, which is the fiber matrix interface. Another defect can be debonding. Debonding means that if you have the reinforcement and then you have the resin inside, and if the this reinforcement is disconnected from the resin, so within the resin, the interaction with the reinforcement with the resin is weakened and it is debonded. So there is no connection between the fiber and the resin. So this will result in the decreased properties of the composite, and it is a failure. And the other one is the interlaminar cracks. So if the cracks are being developed in this direction, these are the interlaminar. So from one laminar to other, or maybe if there are some other laminates connected to this one, and within these, if the cracks are created, such types of cracks are known as interlaminar cracks. So these are the main crack or defects. The last one is the distortion. Distortion means if your laminate is bended because of some residual stresses. So this type of it was meant to be straight, but it is distorted in this direction or in this direction. This is the distortion. This can happen because of improper curing or due to your care. Let's see what are the typical inspection methods for structural health monitoring. First of all, we have the vibration, which used on vibrating the aerostructure and then looking for its defects. Then we have the radiography, which use X-rays. Then we have the acoustic emission, which use the elastic waves produced as a result of crack propagation. Then we have the eddy current, which works under the process, the principle of electromagnetic induction. Then we have the chirography, which use coherent lights or lasers. We have the thermography, which use the radiations given by the surfaces. We have the ultrasonic, which uses high frequency sound waves which are not audible by us, and these are used for defect detection. Then we have the embedded sensors, which are embedded as a part of the composite, and they can be used for structural health monitoring. So every sensor, whenever you see, it will work in a way that if you have a laminate, you have to give some energy to this laminate. This energy can be given by yourself, known as the active system, or this energy can be present naturally by some other process known as the passive method. So this energy is detected by a sensor. So all 8 types have their own sensors which will detect that energy with the basis of its own physics. This sensor will change that physics, transform some physics into some meaningful manner. Typically it is amplification. So this signal has to be amplified to study it for further interpretation. Then you have the post-processing of that transformed data, which can be read by a normal person, and this person will interpret it and decide based on the data received that whether there is a defect or not, what is the location of that defect, what is the size of that defect. If that size is above a threshold level, that laminate will be rejected. Otherwise, this defect will be recorded and it will be monitored next time if it is going through that threshold or not. Vibration-based structural health monitoring can be considered as a discrete or continuous system. The discrete system is modeled as a lumped system like mass, damper, and spring. So this is a simplified way. Otherwise, if it is continuous, it has to be studied using FEA and model analysis. Typical things to consider are the natural frequencies, ramping ratios, strain energies, or modes, and these are compared and analyzed to see if there is a defect in the system or structure or not. So first of the typical sensors, accelerometers, they are normally contact based, but non-contact sensors are the vibrometers. So this is a typical laser Doppler vibrometer which works on the principle of interferometry. They are very sensitive, but they have portability issues. They are very big in size and very expensive as well. This vibration-based structural health monitoring is typically used for moving objects, turbine blades, or machines. Sometimes they are used for big civil structures as well, but the problem is that you need to energize them continuously, and high amplitude, low frequency energizing takes a lot of energy, which is expensive. So also, in order to interpret the results, you need experience and expertise. So you can have these accelerometers embedded as a part of the aerostructure to constantly sense and monitor the condition of the structure without contacting any new setup. So this can be useful as this way. So radiography use the X-rays. These are the electromagnetics of extremely short wavelengths. This is the typical wavelength they have. So what happens is that there is an X-ray source which goes through the structure, and the defect has a decayed photograph on the photographic sheet, and this system can detect all types of cracks. And the new way of doing it is the CT, the computed tomograph. CT scan gives you 3D images, radiographic images, and it can detect in surface deep inside cracks as well. But as X-rays are dangerous for the health, they are hazardous, so this is not recommended for the structures which are near the human interface. And also you need very good safety precautions and trained people to operate these systems. The third one is the acoustic emission. In acoustic emission, it is normally termed as a passive method because you are not giving continuous energy. So it has its own preloaded structure. So what happens if you have a preloaded structure? There are elastic waves emitted if there is a defect. So whenever there is a defect, every system under load has some strain energy in it, and if there is a damage or crack, this strain energy is released in the form of elastic waves. So those elastic waves are detected. So if you see here apparently this is the acoustic emission sensor, and if you see, it is a contact based acoustic emission sensors. But this system, as it is very famous in structural health monitoring, that's why I put it here, and it can easily detect those elastic waves, and it can amplify it, pre-process that data, and it can give you some graphs, and you can decide what is the size of that crack. So it also gives you monitoring. If you have a crack, initially there will be some elastic wave. After some times, if this crack is propagated, this wave, elastic wave, will change its trend, and you can see the crack is getting dangerous or not. So this is a very quick way. You don't have to, and cheap as well, you don't have to use a big amount of money on it because these sensors are cheaper. But also this is good for continuous monitoring. But the problem is that it gives you a binary output. So it is very tough for you to quantify the size of that defect. It gives you an output whether there is a defect or there isn't a defect. Now, the problem is that there are very expensive sensors available which are contactless, and they can measure the elastic wave because elastic waves are very much very low amplitude and low frequency waves, and you need very accurate sensors. And the moment you disconnect the sensor, there is the air inside, and air has the leaking properties. So the sensors, the good sensors are required to measure those elastic waves, and those are very expensive. So at the moment, we don't have the contactless sensors, very common. On that reason, AI is not a non-contact structural health monitoring system. If you have the money to buy those contactless sensors, this can be utilized as a binary output system. And in the future, if you replace these contact-based sensors by embedding them as a structure of the composites, then still you can use them as the acoustic emission structural health monitoring. Eddy currents is the next type. Eddy currents works on the principle of electromagnetic induction. So you have a permanent primary magnet, AC flux is changing, and there is a conductive surface present, which is the your laminate, and eddy currents are produced on this conductive surface. So these eddy currents are affected if they are defects. So eddy currents distribution depend on the surface of the conductive laminate. So this is good for surface and subsurface defects, and the problem with this is that it is only used for conductive material, and also if the surface finish is not good, it can give you errors as well. The next system is the chirography. In chirography, there is a coherent light source incident on the CFRP laminate. Basically, it's a laser which works on the principle of interferometry. So the velocity, the wavelength of the incident wave light has a coherence with the surface present there. So this wavelength is shown as dark and bright images which show you the presence of defects on the surface. So if this is a CFRP laminate with surface cracks there, if we see the chirography image of this surface after the effect of this laser light, there will be some images like that which shows that there are surface defects on this laminate. So it is a replica of hologram. So it's like hologram, and it gives you an image of the surface cracks. So this is a very good method, fast and robust, but the interpretation is complex, so expertise are required to understand this chirography method. The sixth one is the thermography. So thermography uses the surface radiations with the help of a thermal camera. So every surface, when absorbs heat, it re-emits in the form of infrared radiations. So these radiations, with their rate and intensity, give information about that surface. So for example, this radiation can be, thermography can be active or passive, and this example which is shown here, there is the active thermography in which we give heat from external source and then see its effect using the thermal camera. If you don't give the heat and you are naturally watching the thermal image, this is known as the passive thermography. So in this case, you can see that when there is defect, there is a different amount of radiations emitted from the surface. So basically, the energy radiations given out based on the Stephen-Boltzmann law gives out that what type of surface it is, and it gives you very different types of defects. Like this one is a subsurface defect. So similarly, you can find out the delaminations or debondings. So with the modern technology available now, we have a very high resolution thermal cameras available, and you can measure up to a very good accuracy the surface characteristics, which involves the debondings or delaminations or cracks. So this is an image taken from my work done by my MS student for a thermography of railroad. So there is a crack. It is about 0.5 millimeter deep crack, and the gray image is done after the post-processing of this thermal image, and the intensity at this specific amount is telling that it is different from all the intensities or the pixel frequencies. So this is telling you that there is some crack on that surface. So this is the same work presented in the same conference. Another work shown by done by my PhD student Ms. Zara. So in this work she used the CFRP laminates. These are the pre-preg laminates. We worked with the collaboration of UIT Norway. In that work, this is a specimen ball dropped on the carbon fiber polymer laminates, and this is the spot of that dropped image using a thermal high resolution camera. So you can see there was a small amount of energy released when we dropped a ball on the surface. So this was a passive thermography, and we done the same with the help of the numerical model, and we saw that there was this 2.6 degree change in rise in temperature. It was a very fast rise in temperature, and it vanished away very quickly. So you need high resolution and high speed thermal cameras in order to detect such changes. But with the modern technology available, these methods are very effective. They are non-contact, and they can have a very good record of all the changes happening in your CFRP laminates. The ultrasonic based structural health monitoring is the most common one. Typical ultrasonic testing works with a contact based transducer which detects the defect, but new ultrasonic methods are non-contact based. Basically, guided waves is the phenomenon in which low frequency waves are transmitted through large surfaces, and these waves can be detected using non-contact methods. Another way of ultrasonic testing is the bulk waves, which are high frequency complex waves which are attenuated very fast. Guided waves are good for long structure. Bulk waves are good for complex structures and short attenuating surfaces. So laser ultrasonics is a modification of ultrasonics in which you use a laser as a source. It is a pulse laser which produces high frequency ultrasound in the surface, and then you can use LDV, for example, the laser Doppler vibrometer, to receive those. So this is known as laser ultrasonics. These typically produce bulk waves, and these are good for short distances. The other way, this is another example where you can see the surface waves producing on the surface and on the complex geometry. These are reflected back as many other different types of waves. Another orientation of ultrasonics is the EMATs. These are the electromagnetic acoustics transducers. They are the modified form of eddy current. So they, based on the Lorentz force produced, they produce ultrasonics in conductive surfaces again. And these are good in a way that they are non-contact and they don't need a glycerine or other couplant to be used with the typical piezoelectric sensors. So it works without EMATs. So we are working on these to detect railroads cracks, and in future I will use it for CFRP laminates as well. Then last we have the air coupled sensors, which can work on larger distances away from the surface as compared to EMATs. But the problem with them is that the amplitude and the strength of the guided waves should be very good because they are in the air, and in the air the intensity of the signal is attenuated very quickly. Then we have the embedded sensors. So you make the sensor a part of the manufacturing process and they become a part of the structure. And typically they measure the strain. So these sensors inside the structure, which is preloaded, they can, for example, be optical fibers. So you can see the transverse cracks are produced here, and optical fibers will sense that strain and give the data to the structural health monitoring. Second is the fiber drag grating. They can not only be used for tensile forces or loadings, but they can also use for temperature. So these are the temperature sensors embedded in the laminate, and they will detect if there are some thermal changes or thermal strains. The typical piezoelectric sensors can be made the part of the laminate, and they can be good for measuring vibrations or strains. So these three typical structural health monitoring system can have their sensors embedded in the laminates to have a structural health monitoring. Typically, embedded sensors are not are contact based, but you don't have to make a new setup for measuring some physical energy there. So you can call them contactless in a way that you don't have to do any setup for these sensors, and they are cheaper. This makes them cheaper than the other setups, and also there is no setup time. So they are good on those things, but also these are compromise on the strength and homogeneity of the structure. So these are the favorite locations for crack propagation and failure structure. The last part of my presentation is related to the post-processing. So in the post-processing, there are also new trends. The current trends were probability of detection curves. So based on the knowledge of different time histories of the product life, some curves are generated, and these models and curves give you an idea if there is a crack present or not. So for example, a typical POD curve is of this shape. So if you measure some signal and the signal comes here, it means that the crack is not available. And if the signal is somewhere here, it means that there is a more probability that there is a crack. And if this region is very steep, so most of the time results don't come in this region. So based on this curve, you can decide whether you have to whether there is a crack of that threshold level or not. So these curves are based on the knowledge of the user. So basically these curves are used as the reliability of your test. So every inspection system can have its own POD curve, and for a person at field, he has just to look onto that printed curve and he can decide whether there is a damage or defect of a specific size. And now these POD curves have been empowered by the use of machine learning and new trends. But if you are not expert enough, you cannot interpret these POD curves. So talking about the machine learning and artificial intelligence in this new era, the artificial intelligence has and the new computation processing powers, we have the new option to work with the modified and well-developed POD curves, and even other statistical models can be enhanced, so the human interface or the personal errors are decreased, and we are moving towards automation. So all the structural health monitoring systems are empowered by the post-processing new techniques, and we have more reliability added to all the. So now I will conclude here that the structural health monitoring starts from the manufacturing of the CFRP laminate. So when you do the NDT, that data is required for your structural health monitoring. And overall cost of the product is decreased when you do the structural health monitoring. You can use a single method of structural health monitoring or a combination of methods depending on your applications and use. So you have to decide which monitoring method is suitable for you depending on the application of CFRP, where you are using it. So what is the life expectancy of your laminate, then if you have the accessibility to the laminate structure or not, and also how much resources you have available. So these are the main factors which define your monitoring methods. So that's it. So now I welcome you for any questions and answers. Thank you very much.